All right. Well, for chapter 9 is about chemical bonding. Like I said, bonding is sort of one of the most fundamental principles or activities in chemistry because you can't form molecules or compounds without bonding. So, understanding bonding is a very important part of studying chemistry. um, First of all, there are different types of chemical bonds depending on what types of atoms are being bonded together. And we've looked to some degree at some of them. We're familiar with covalent bonding and ionic bonding, at least in general terms. And well, there's another type of bonding that we haven't really discussed yet, but it's metallic bonding, and that occurs when you have a chunk of metal. What is it that holds the individual atoms of the metal together with each other? And that's not it's kind of a little bit different in concept from ionic and covalent bonding, because for one thing, it usually involves elements of the same atoms of the same element, and you're not forming compounds that way. But anyway, we'll get to that in more detail a little bit later. First of all, let's start with the basics of why does bonding occur. And a simplified version, which is good enough for most purposes, is that bonding occurs because atoms are more stable that way. You'll have elements that want to achieve a noble gas configuration. And electron configuration, that is. And they don't have a noble gas electron configuration on their own. But a noble gas electron configuration would allow them to be very stable, and so they tend to want to achieve that situation. If they don't have a noble gas electron configuration on their own, then how do they get to one? Well, generally, they can get to a noble gas electron configuration by either gaining or losing electrons to another atom, or by sharing electrons with another atom. And that's what most bonding is actually about: gaining or losing electrons or sharing them with another atom. And so basically, to achieve a noble gas electron configuration by gaining, losing, or sharing valence electrons. And that's what most bonding really consists of. A less simplified version is according to Coulomb's law. When atoms approach, the electrons of one atom can be attracted to the nucleus of the other atom, and vice versa. Okay, and so the other atom can also be attracted to the first atom. But the problem is that the electrons of both of these atoms are around the outside of the atoms. And so in order to interact with anything else, you kind of have to get by the electrons. And the electrons of any given atom should repel the electrons of any other given atom. And it should be the same for the nuclei, because the nuclei are positively charged, and like charges repel. But actually, it is possible for them to get close to each other if the negative charges, like the electrons, are between positive charges, like the nuclei. Okay, so, and that is really what a bond, or covalent bond anyway, consists of, is sharing of electrons between positively charged nuclei. So if the interactions lead to a lowering of the potential energy between the charged particles, the bond will form. And that's probably enough of a background for our purposes for why bonds formed. The types of bonds would be some of the ones we're familiar with: ionic bonds, and that would be between metal and nonmetals. And that involves a transfer of electrons from the metal to the nonmetals. So the metal ends up forming a positive ion, and the nonmetal ends up forming a negative ion, the two of which are then attracted to each other, and that attraction between the positive and negative ions is what's known as an ionic bond. Covalent occurs between nonmetals, and that amounts to a sharing of valence electrons between two atoms. And then there's metallic. And that occurs within metals. And that's effectively a kind of pooling of electrons. That is, the nuclei of the metal atoms are more or less fixed in place, but the valence electrons are not tightly held, and they're sort of able to move and flow all over the place. They're sort of like jointly shared by all of the nuclei in the entire chunk of metal. So what you've got is, for this last type, you've got fixed nuclei surrounded by a sea of mobile valence electrons. And what they call this is delocalization of the valence electrons. In other words, they don't belong to any one atom in the sample of metal. They're able to move all over the place very easily. And okay, if you're following the Lewis model of bonding, which is what we're doing in this chapter, G.N. Lewis was a chemist who was very interested in electrons. Lewis's name comes up several times in general chemistry, and every time it does, it has to do with electrons. And one of the cases where it comes up is right here in bonding. And his Lewis's model of bonding essentially emphasized the electrons. Where do they start out? Where do they end up? And it actually makes for a very convenient way to track what happens with the electrons during the bonding process and why the bonding process occurs, again, by watching the electrons. We start out looking at Lewis symbols. And Lewis symbols are basically symbols for individual atoms or, atoms or ions, which represent the valence electrons with dots around the symbol of the element. And representing the electrons, the convention is to use the symbol for the element. And you represent the valence electrons as dots around that symbol. And the convention is that you confine the dots to areas that are directly above or below, or directly to the left or to the right of the symbol. And you would use a maximum of 2 electrons in each of those 4 positions. Or in other words, any given element or ion would normally end up with a maximum total of 8 electrons around it. And this makes sense because, as we've seen in previous chapters, ion formation, when an atom forms an ion, what it's essentially trying to do is reach the electron configuration of one of the noble gases. The noble gases have 8 electrons in their valence shell, except for helium, which has 2. And so it makes sense that a full valence shell would correspond to 8 electrons. And so we end up with 8 electrons maximum around the Lewis symbol. So this is because atoms with 8 valence electrons are stable. And examples of those would be noble gases or main group elements ions. And this is known as the octet rule. Or the duet rule in reference to hydrogen and helium. And what it means is that in bonding, atoms from other groups will try to get 8 electrons around themselves by gaining, losing, or sharing valence electrons. Okay, so basically you're trying to get an octet of electrons around yourself by gaining, losing, or sharing electrons with other atoms or other ions. Bonding in these terms is just sharing or transfer of electrons. Valence electrons, that is. In order to get a stable electron configuration for bonding atoms. Transfer of electrons between a metal and a nonmetal is known as ionic bonding. Sharing of valence electrons between atoms of nonmetals is covalent bonding. Okay, so to start out with, we'll have a look at ionic bonding. Okay, and this will be particularly with regard to Lewis structures first. And then lattice energy we'll get into. Lewis structures are what you get when you take Lewis symbols and sort of piece them together to form a compound or a molecule. So Lewis symbols are, technically for atoms or monatomic ions, whereas Lewis structures are when you piece two or more Lewis symbols together to form a larger structure. And Lewis structures can be applied to ions also. Or Lewis symbols, technically. And because they show you why basically certain ions form with certain charges. So losing electrons like metals do just means moving some of the dots over to the nonmetals. And so losing electrons is like losing dots in terms of Lewis structures. Gaining electrons is like gaining dots. And of course, sharing electrons is like sharing the dots. So for example, in the case of sodium chloride, sodium, the element, would be written as Na with one dot because it has one valence electron. It doesn't really matter where you put that dot, but it should go above, below, to the left, or to the right of the symbol. Doing sort of segregating off the dots into certain areas around the symbol allows us to count the dots quickly, at a glance, to understand how many electrons something has at a glance. If I were to write symbols with the dots any old place, I could write chlorine with this number of dots, and writing them like that, you'd have to sit there and count the dots to tell whether that's a chlorine atom or a chlorine ion. So a chlorine atom would look like this. Chlorine ion, with 7 electrons, chlorine ion could look like this. That's not really a big difference in the way they look. And looking at them at a glance, you can't really tell. If you do it the way that we're supposed to do it, though, a chlorine atom will look like this. So just the fact that you can see, oh, there's a dot missing there, but there's only one dot missing, so that means it's got 7 electrons. You can tell that just by looking at it at a glance without actually having to count the electrons. The chloride ion would look like this, with essentially all of the dots there. And the point is, you can tell that all of the dots there are there at a glance without having to count them. Okay, so for sodium, It's going to be Na with one dot. Again, it can go above, below, to the left, or to the right. I'm going to put it there. Sometimes, you may prefer to draw the electrons in certain places just because of the way the atoms or ions are going to end up fitting together when you make a structure out of them. And, as you get more practice writing these things, you'll sort of tend to learn which configurations make it most obvious what's going to happen and which ones don't. And you may have certain preferences, but as long as you conform to the rules, you'll be okay. Okay, so in this case, it's fairly easy to see what happens here. Chlorine needs one electron to reach an octet. Sodium has one electron that it doesn't have a very firm grip on, and so we end up with this. Sodium loses its one valence electron. Now, when sodium loses its one valence electron, it now has an octet, but that octet is in the shell that's one less than the valence shell. So when we're dealing with Lewis structures, we always stick with the original valence shell. So the idea is that once sodium loses that one electron in the third shell, it now no longer has a valence shell. At least it doesn't have the original valence shell anymore. So a sodium plus ion in Lewis structure terms would be represented as the symbol for sodium with no dots around it because it has no valence electrons. The original valence shell is gone. Okay, so sodium symbol here has no dots because the original valence shell is gone. And the chlorine has gained one dot, and it now has an octet. And the convention is to put ions inside square brackets, just as kind of a symbol that, yeah, this is an ion, not an atom. Although, chlorine with 8 electrons, that right there should tell you that it's an ion. Okay, and so now you can see because of the plus and the minus, these two ions are attracted to each other, and that would be an ionic bond. And chlorine has an octet of valence electrons around it now, and that makes it stable. Looking at the electron configurations, again, sodium has 11 electrons, so it's going to have a configuration of 1s2, 2s2, 2p6, 3s1. And that is equivalent to neon with the 3s electron added on. Sodium plus has lost an electron, so it has 10 electrons total. And that's just 1s2, 2s2, 2p6. And that would be just the configuration of neon. So as you can see here, sodium loses its entire valence shell, but now it has an octet in the next shell down. We don't represent that shell in the Lewis structure because, again, we stick with the original valence shell, but that's handy to know that that's basically why the sodium is so stable as an ion, but not as an atom. For the chlorine, we have 1s2, 2s2, 2p6, 3s2, 3p5, which is only one electron short of the configuration of argon, which is why when chlorine gains an electron, it becomes so stable. It's now 1s2, 2s2, 2p6, 3s2, 3p6 has an octet in its outer shell, and this is the same electron configuration as argon. Okay, and so it's stable. If you look at something a little different, like calcium chloride, we find that we have calcium with 2 valence electrons, and we're combining it with chlorine, each of which has 7 valence electrons. So each chlorine only needs 1 more electron. So one of calcium's electrons goes to one chlorine, and it takes a second one to take in calcium's other electron, because calcium essentially is not going to be stable until it gets rid of both of those valence electrons. And so if chlorine happens to be the only thing around to combine with calcium, then calcium is going to have to give 1 valence electron to one chlorine and the other valence electron to another chlorine. And so what we end up with is calcium ion with a 2+ charge. And again, it's lost its original valence shell. So in Lewis structure terms, we consider that as having no valence shell. And that would combine with 2 Cl minuses. So you could write that like this. So calcium, the element, has 20 electrons, and that puts it 2 electrons beyond argon, which has 18 electrons. So the configuration for calcium metal will be Ca, will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And that is equivalent to being argon plus the 4s2. And losing that 4s2, those 2 electrons in the 4s orbital, that leaves us with the configuration of argon, and that's why calcium wants to form +2 ions and not just +1 ions. And also notice that calcium +2 has not only the same configuration as argon, but it has an octet in its new valence shell. So it's stable. And for the chlorine, we can just see up above. That works the same way as it did before. Each chlorine gains 1 electron and adopts the same electron configuration as argon. Okay, we're up to lattice energy now, but I see that we're at 29 minutes for this segment, so I think I'll leave the lattice energy for the next one. See